अभी अभी क्लासेस वगैरह लगी हैं, तो उसके अंदर जो आपने मतलब जो एक्स्ट्रा स्लाइड्स वगैरह बनाई हुई है, उसकी पीपीटीज वगैरह एलएमएस पे कहाँ पे हैं?
Let me show you that. Where is my LMS? Okay, you can see my screen, right?
Yes, ma'am.
So this is UPH, Applied Physics. Go down, 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 down. Video class lectures by Dr. Sunil Devi. Go there. And here, इस lecture में जैसे oscillation and waves के लिए हमने जो PPT की थी, it's available here, right? You click on here, and इसकी जो PPT है, you'll get the PPT. उसके बाद में जितने भी क्लास लेक्चर हैं, क्लास लेक्चर 1 इंट्रोडक्टरी था, एंड आई डिडंट नो कि वो ऑटोमेटिकली रिकॉर्ड नहीं हो रहा था. मतलब आई हैड टू press record button manually to start recording on Zoom, but we didn't cover anything except the syllabus क्या होगा, evaluation scheme क्या होगा. उसके अलावा जो बाकी लेक्चर्स हैं, they are there. Acoustics का जब हमने स्टार्ट किया है, इसकी जो बुक है एक्चुअल में इट्स वेरी ओल्ड बुक. लाइब्रेरी में उसकी काफी सारी कॉपीज हैं, वो भी काफी पुरानी है, तो बच्चों ने उसमें इनका बहुत सारा मार्क किया हुआ है. सो आई हैव अपलोडेड दैट बुक आल्सो हियर, द स्कैन ऑफ दैट बुक. और उसमें जो रेलिवेंट सेक्शंस हैं वो मैंने यहाँ पे मेंशन किए हुए हैं कि आपको कौन कौन से सेक्शंस जो हैं वो रीड करने हैं.
ओके मैम. और मैम जो अकॉस्टिक्स की जो पीपीटी होगी वो भी डालोगे आपके बाद में?
इट्स देयर.
ओके, ठीक है मैम.
पीपीटी जो हम लोग अभी यूज कर रहे हैं, दिस इज आल्सो अवेलेबल देयर.
और मैम जो भी एमएसटी वगैरह होंगे उनमें से जितने भी ऑलमोस्ट क्वेश्चन होंगे वो पीपीटी के रिगार्डिंग होंगे कि हमें बुक से भी एक्स्ट्रा पढ़ना पड़ेगा?
पीपीटीज आर एनफ, बट मैनी टाइम्स क्या होता है पीपीटीज में जो मैं लिखती हूँ, आई डोंट राइट एवरीथिंग दैट आई स्पीक, राइट? क्योंकि पीपीटीज आर काइंड ऑफ एब्स्ट्रैक्ट फॉर्म, सो यू हैव टू, अगर कोई थ्योरी का क्वेश्चन है देन यू हैव टू राइट सम काइंड ऑफ स्टोरी अबाउट इट, राइट? जैसे अगर मैं एलसी सर्किट का एक्सप्लेन कर रही हूँ. हाँ जी
मैम, मेन पॉइंट्स तो यही होंगे ना, मतलब इनसे सिलेबस तो यही है एक तरह से?
हाँ जी, हाँ जी, ये सिलेबस आपका इसमें पूरा कवर्ड है.
ठीक है, थैंक यू मैम.
हाँ जी, मतलब इससे बाहर आपके सिलेबस में कुछ भी नहीं आएगा. मयंक, एमएसटी की बेटा टेंटेटिव डेट तो आई डोंट नो.
एक्सक्यूज मी मैम.
हाँ जी
मैम, जो भी आपने बोला अकॉस्टिक्स के लिए, तो जो आपने पहली पीडीएफ ले रखी थी सर्वे एंड ज्योइट की, उससे नहीं पढ़ना वो?
नहीं बच्चे, अकाउस्टिक्स सर्वे एंड ज्योइट में शायद दिया भी नहीं है बहुत.
अच्छा, ओके मैम.
अकाउस्टिक्स की जो बुक वो सर्वे एंड ज्योइट की सिर्फ वेव्स एंड ऑसिलेशंस के लिए थी, एंड वेव्स एंड ऑसिलेशंस की जो पीपीटी मैंने अपलोड की है उसमें जो लास्ट वाली स्लाइड है उसमें स्पेसिफाई किया हुआ कि सर्वे एंड ज्योइट के कौन कौन से पेजेस या सेक्शंस जो हैं वो आपको कवर करने हैं.
ओके मैम,
हाँ जी,
थैंक यू.
हाँ जी. श्रेया,
excuse me ma'am, वो जो tune sheets है, are they similar to what we'll get in the exams?
they will be kind of similar. If you did really understood your tutorials, then you should be able to solve the questions in exam also.
Should we try to do harder questions for practice?
You should try at least some questions. मतलब exactly ऐसा नहीं होगा कि tune sheet में से as it is exam में आ जाए. That's not going to happen.
But the difficulty level is similar?
More or less similar.
Okay, thank you ma'am.
Welcome. Is it second Mayank or the same Mayank?
I think the same, ma'am.
Okay. Actually, there are two Mayank Sharma with the same name. So.
Okay.
Okay, let's start the class now. So in the last class, we did talk about the reverberation time. I'll just revise it very quickly, because I am not able to convert it into MP4. So we defined reverberation time as the time during which your intensity falls to 1/1,000,000th of the initial intensity when the speaker has stopped speaking. Or this is also defined Chirag, yeah, you can refer from the tune sheets, but you still need to do some extra questions, because they will not be exactly the similar questions. But if you have understood the concepts that are used in the tutorial sheet, you will be able to solve the exams. Okay, coming back to the present thing. Reverberation time we define as the time in which your intensity decays to 1/1,000,000th of initial intensity when the source has stopped making the sound. Or this is also defined as a time taken by the intensity to reduce to limit of human audibility. स्पीकर ने बोलना स्टॉप कर दिया है, उसके बाद में कितने टाइम के बाद उसकी जो साउंड है वो इनऑडिबल हो जाएगी, that is also called as your reverberation time. Then we talked about absorption coefficient. Sound being a mechanical wave, it follows all the rules of waves. It gets reflected, it gets transmitted, it gets absorbed also. Similarly, in that case, every object on which your sound is falling will have certain absorption coefficient, which basically means that किसी भी object पे आपकी जो sound intensity incident होगी, a fraction of that intensity will be absorbed and a fraction of that intensity will be reflected. How much will be that fraction? That will depend on a lot of parameters. For example, if some material is extremely porous material, if you have some kind of wall hanging, you have carpets and those kind of material, they are extremely porous, so they have high absorption coefficient. Whereas hard surfaces and shiny surfaces such as your bricks and other material, they will have smaller absorption coefficient. Absorption coefficient, if you define it, this is defined as the sound energy absorbed by the object divided by sound energy incident on object. And the term in the denominator many times is written in another form, which is basically the sound energy absorbed by a perfect absorber, which has the same area as that of object that you are talking about. आपका जो perfect absorber होगा, which has the same surface area as that of this object here, वो कितनी sound energy absorb करेगा. Remember, perfect absorber, we said that a window, an open window is a perfect absorber. Sabine, the reason for that is because absorption coefficient is going to be a fractional number. The maximum value of absorption coefficient can be equal to 1. It is going to, the value of absorption coefficient is going to lie between 0 and 1. We need some kind of reference to define absorption coefficient. For example, if I say that wood has absorption coefficient 0.2, with respect to what? It has absorption coefficient 0.2, right? As I said before, everything that we measure, whether it's kilogram, whether it's length, whether it's time, there is some reference with respect to which we define all these variables. Similar to that, for absorption coefficient also, there is a reference, and that reference was basically defined by Sabine. Sabine being the person who actually started the concept of architectural acoustics. He defined your reference as 1 square feet of open window. He said that there will be a reference and that reference will be your 1 square feet.
Shreya and Mayank has some doubts.
हाँ जी, उनको unmute कर दीजिए.
Okay.
And this is called as 1 Sabine, after the person who defined it.
Shreya
So,
and Mayank, you can ask.
Excuse me, ma'am.
हाँ जी.
मैम, तो जो ये अल्फा एब्जॉर्प्शन कांस्टेंट, इसकी वैल्यू हमेशा 1 से कम ही रहेगी ना?
हाँ जी. Maximum it can have value 1 for open
Okay.
window or a perfect absorber. हाँ जी, Shreya. I think it was probably by mistake. So the reference for measuring the absorption coefficient was defined 1 square feet of open window, and absorption coefficient of all other materials was defined with respect to this. And the absorption coefficient of open window, for open window, your absorption coefficient is 1. The reason being that if your window is open, all the sound intensity that will be incident on this open window, it will be totally transmitted through the window, which is basically equivalent to saying that your all sound intensity has been absorbed and there is no reflection of the sound. And hence you can take the absorption coefficient for open window to be equal to 1. Then we said that because in a room there are going to be a very large number of objects present, in that case, what we can do is that rather than defining the absorption coefficient of every single object, you can define an average absorption coefficient. And that average absorption coefficient, we said that let's denote it by alpha bar. And I can say that what I can do is that I can multiply the absorption coefficient of every object with the surface area, the geometrical surface area. There are going to be two things that we are going to talk about. One is effective surface area and one is geometrical surface area. Geometrical surface area you are already familiar with. For example, if you have a rectangle, then the geometrical surface area will be length into breadth. So this S here is your geometrical surface area for first object, and I'm multiplying it with the absorption coefficient of first object. And then I can do it for all the objects that are present in that room. So Harsh, aapka doubt hai bachche? And then we need to divide it by the surface area of all the objects that we are talking about. This will just a second. This will give us the average absorption coefficient of a room. For example, if you talk about a classroom, you have a large number of tables, you have large number of chairs, there are large number of audience or students present, there is going to be whiteboard, there are going to be walls, there is going to be floor, ceiling, curtain, carpet, everything that is present in the room. So you take the surface area of each term and you multiply with the absorption coefficient of that particular surface area. Hanji Saharsh.
मैम अगर हम अज्यूम करें कि अल्फा कभी ग्रेटर देन 1 हो जाए तो उसका मतलब क्या होगा मैम?
It's not possible.
मैम वो एनर्जी कंजर्वेशन को वायलेट करेगा फिर? मतलब वो जिस पे जितनी इंटेंसिटी उस पे फॉल कर रही है,
आपकी जितनी एनर्जी इंसिडेंट थी उससे ज्यादा एनर्जी
एब्जॉर्ब कर रहा है.
That is not possible.
ओह, एनर्जी कंजर्वेशन वायलेट कर रहा है.
हाँ जी, basically you are saying that you are generating energy after the
yes ma'am
energy. Can't do that.
Okay ma'am.
Yes. So I can further then in this case rewrite this expression as alpha bar summation over I SI, where I'm defining this as summation SI, and then I can say that let's do summation over here also. Over all the objects, I represents your ith object over here. There are now a couple of terms which we'll discuss related to this. There is something which is, we have defined alpha as the absorption coefficient of particular element which has the surface area S. This is called as effective surface area.
Ma'am, Anmol has some doubt.
Hanji, Hanji. एक बार कर दीजिए. And this is also called as absorbing power of that particular object. How much that.
Ma'am, you have unmuted me instead.
Ma'am, alpha जो होगा 1 maximum black bodies के cases में होगा.
Alpha has, sorry I didn't get you.
Alpha maximum 1 black bodies के cases में होगा.
Alpha 1. No, we are not talking about electromagnetic radiation. We are talking about sound waves.
Sure.
Yes. So your alpha is equal to 1 for an open window or a perfect absorber of sound. So this term alpha S is called as, here this S is your geometrical surface area. If I multiply it by the absorption coefficient, then it gives me effective surface area or effective absorbing surface area. You can call it that also, or the absorbing power of that particular object here. If you talk about the unit of it as such, because alpha does not have any units, it's a coefficient, S has the unit of surface area, then it has the units of meter square, but usually this is represented in open window unit. I'll tell you why. If you multiply this, you get basically another surface area. And that surface area, you can say that is the surface area for an open window which has absorption coefficient equal to 1. आप इसको इससे multiply करोगे, आपको मिल जाएगा एक surface area, and then you can say that that is the surface area of open window, because your open window will have absorption coefficient equal to 1. So either, let's say, you can have, if let's say I have this 100 meters square and my alpha is 0.1, right? So I can say that I have a surface area 100 meters square which has an absorption coefficient of 0.1. Or in other words, I can say that I have an open window which has a surface area of 10 meters square, right? So both of them will have the same absorbing power, and that is the reason why this is written in open window unit many times, right? Now let's talk about the next, which is your Sabine's formula. So Sabine, he was a professor in Harvard University. There was a room which had exceptionally large reverberation time, and he was given the job to reduce the reverberation time of that particular lecture hall. So what he did was that he took a listener with him, and then by changing the objects inside the room, they observed the change in the reverberation time of the room. And they had certain observations, and those observations was that your reverberation time is going to depend on the reflecting property of walls or floor or ceiling or any other object that is present in the room. The second observation he made was that your reverberation time in other way is going to depend on the absorbing power of the various surfaces, such as, for example, your wall, your ceiling, or any other object. Just give me a second. 1 second, sorry about that. Sorry about that, Vijay. So I was saying that then they did a lot of permutations and combinations, and there were certain observations that they made. And one of their observations was that your reverberation time, where did my pen go? Let's denote the reverberation time by T. He found out that your reverberation time is going to depend on the reflecting property of the material. Which basically means that it is going to depend on the absorbing power of the materials. In other words, you can say the same thing. Another important observation was that your reverberation time is independent of the position of source and the listener, which basically means that if you are sitting in a classroom, it doesn't matter if the instructor is standing in front of the class, or if he or she is standing in the middle of the class, or if he or she is standing in the very far back side of the class. your reverberation time of the room is going to remain the same. And similarly, if let's say in the classroom, there are 100 students sitting in that classroom, it doesn't matter where those 100 students are sitting. They could be sitting, just all of them in the very front, all of them could be sitting in the middle of the classroom, or all of them could be sitting in the end of the classroom. So reverberation time is going to remain the same, which basically means that this will be independent of position of source. And here source means the source of sound and listener. And then he found out that if you have a room, then this is going to be directly proportional to the volume of the room. And this is going to be inversely proportional to the effective surface area. And let's call that A effective, which is basically equal to alpha multiplied by S. And if there are large number of objects present, then they will have the summation sign over here. Aviral, बच्चे आपके कोई डाउट है?
Yes, ma'am. Ma'am, आपने बोला कि position of source does not change reverberation time, है ना?
Yes.
Ma'am, but अगर जैसे randomly हमने room के अंदर speaker रखा हुआ है कोई सा, तो उसको अगर corner के पास लेके जाते तो उसकी आवाज better हो जाती है, reverb बढ़ जाता है.
No, shouldn't happen. अगर वो because with this we are making assumption that your sound is getting equally diffused in the room.
Ma'am, but source तो point ही होगा ना हमेशा.
Yes, source is always going to be a kind of point source.
So
if you are saying that, because that is if you are talking about the regular speakers that we buy for our home, the surround system, are you talking about those kind of speaker or in general?
Single speaker, ma'am, एक single speaker, Bluetooth speaker.
In a single speaker. If you keep it in a room, then you are saying that it will be dependent on the position of the source.
Yes, ma'am. Corner पे रखते हैं तो थोड़ा reverb ज़्यादा आता है, थोड़ी आवाज better आती है.
No, that's probably your perception. It shouldn't matter.
Okay.
I'm going to find out some kind of simulations if I can find out for that, and let's see if I can find that out. I will play that in the next lecture, but it shouldn't matter.
Sure.
Yeah.
Okay. Thank you.
Okay. Another students, Mayank.
I also have the same question.
Okay. Let me get some simulation for that.
And I think he meant if we face the speaker towards the wall when it's in the corner.
Okay, then that's a different story. If you put the speaker face towards the wall, then that's the different thing.
Okay, ma'am.
Yeah, no, you can't do that. Because remember I said that we are saying that we are assuming that your sound is diffusing throughout the room uniformly. So if you are saying that, okay, I'm going to put my finger around my mouth and then I'm going to speak, then that's not going to be equal, your reverberation time. Because then we are saying that, right? When your speaker speaks the sound, then your sound is going to travel in the form of a cone, right?
Okay,
so if you put it in this direction, then your sound is not getting diffused properly.
Okay, thank you.
Yeah. Another observation.
Sorry, I'm sorry. I just had a doubt. Ma'am, so in terms of music production, if you're adding a reverberation effect, then even in that one, there's this option to add a mid and a side, and it gives very, very differing reverberation options. So,
if you, what did you say? Can you repeat that? You are talking about music, and then
in terms of music production, when you have to add a reverberation effect.
Okay.
The parameters used are those two, similar to like assuming you are standing in a room, right? And so in those parameters, there are options that options between a mid and a side. As in, if someone's standing in the middle of the room and someone's standing on a corner of a room, and you can change the number of sides of the room and how large the room is, but the basic proportions remain the same. So, ma'am, how does that happen? Like, why, like, if the options, if there wasn't a difference between the middle and the side of the room, then, ma'am, because the sound created, the effect created by that is very different from each other.
Okay. Because if you're talking about a music room, right? In the music room, there are not a lot of absorbing material, right? Ideally, where a recording of music happens, if you talk about the professional music studios, in those places, your reverberation time is usually kept minimum, where the singer is recording his or her music or the song, right? The reason being that because you wouldn't want to hear the echoes that are coming from there. And your second question is that you are saying that while doing some editing, you can assume singer to be standing in the middle or in the corner of the room, and that would change it.
No, that the software itself, like the software itself changes the sound that produces.
Yes, if you change the number, if you change the size of the room and all those things, then it will change the sound basically, because then you are changing the volume and you are changing the surface area. If you also change the number of audience, that would also change your reverberation time.
Right, ma'am.
Yes.
But essentially, if someone is standing in the middle of the room and on the corner of the room in very similar conditions, the reverberation time is going to be the same.
Yes, it should be same according to Sabine.
Okay. Okay. Thank you.
Yeah. He also concluded another thing, and that was that your reverberation time would be independent of the shape of the room, if your sound is properly diffused, right?
And one more doubt, student.
Hanji.
Devanshu.
Ma'am, is reverberation, can we call it as echo?
No, we discussed that. Reverberation and echo, there is no sharp boundary to define reverberation and echo. So it's our perception. For example, some people say that if there are different ways of defining it. One says that if the reflections are happening from the surfaces which are less than 17 meter away, 17 meter away from the speaker, then there will be reverberation. And if it is more than 17 meter, then it will be echo. The another way to say is that because if your surface is close to you, then the reflected sound reaches to your ear within a certain amount of time. Remember, our mind can distinguish two sounds if there is certain time gap between two. And that time gap is many times defined as 1/10th of second. It is many times defined as 5 millisecond. So, which basically means that if I'm hearing a sound, and if I hear the reflection of sound within 1/10th of second or within 5 millisecond, then that sound will superimpose on the direct sound and it will sound to us like a single sound. Whereas if let's say I'm hearing something and the reflected sound comes after 1 second, when you shout in the hills, this is what happens, then our mind can separate these two sounds. It can say, distinguish between these two sounds, and then that would be your echo. So that would be your fundamental difference between echo and reverberation.
मैम एक डाउट था।
हाँ जी बच्चे बताइए।
मैम जो प्रोड्यूस कर रहा है साउंड, उसकी बॉडी भी तो एब्जॉर्ब करेगी कुछ ना कुछ, तो हम उसको अकाउंट में लेते हैं?
हाँ जी बिल्कुल लेते हैं। Everything that is present in the room is going to act as an absorber.
Okay.
हाँ जी। बाकी लोगों के भी बताइए।
Basically, we are saying that reverberation and echo are just same. The difference is what our mind creates.
Exactly. Are we able to differentiate between the reflected sound and the direct sound that we are hearing? If we are able to differentiate them, then that is going to be echo. If we don't, then that's reverberation.
Okay, ma'am. Thank you.
Yeah. To remove this sign of proportionality, a constant is there, and that is 0.05 V, and then you have this number here. And here you need to note that your volume has to be in feet cube, your surface area has to be in feet square. And I went back, and this has to be in feet square. If your units are SI units, then this would be equal to 0.162 V over S. Many times it's taken as 1, or many times it's taken as 2. Now your volume would be in meter cube, and your surface area would be in meter square. You'll see that why does that difference come out? It's basically because your sound of your velocity of sound is different in feet per second and meter per second, right? It's 1120 feet per second. If you convert it into meter, it's going to be somewhere around 341.4 meter per second or something. And that factor comes here into this number over here. And that is the reason this constant of proportionality is different depending on the units that you are using here. Okay, so this was totally based on the experimental, or you can say that the observations that were made by Sabine. If this formula has certain limitations, and if we talk about those limitations, the first limitation would be if I have
Excuse me, ma'am.
हाँ जी बच्चे.
मैम ये आपने बोला कि ऐसा यूनिट और उसमें डिफरेंस है, तो अल्फा की वैल्यू दोनों में सेम रहेगी या चेंज होगी?
Alpha is the same because this is ratio of sound energy absorbed by the sound energy incident, right? तो आपकी एनर्जी की जो आप यूनिट ले रहे हो, अगर आप SI यूनिट ले रहे हो तो SI में कैंसिल हो जाएंगे, right?
Okay, ma'am.
Yeah.
Ma'am, another one. I think Manav asked about.
हाँ जी.
मैम जी इसका कांस्टेंट है वो वेलोसिटी ऑफ साउंड पे डिपेंड कर रहा है.
हाँ जी.
तो इसका मतलब तो ये भी है कि जो टेम्परेचर होगा वो एक एक्सटेंट तक उस पे भी डिपेंड करेगा.
Yes, there are a lot of assumptions that we are making now. We are assuming that your absorption coefficient, for example, is independent of angle of incidence. We are making the assumption that your absorption coefficient is independent of frequency also. So there are a lot of factors on which it is going to depend, right? Temperature, you very correctly pointed out, temperature is also going to be a factor there.
Yes, ma'am.
So
okay, thank you.
There are a lot of assumptions that are going in there, right? Okay, so if you talk about the limitation of this expression over here, first is, for example, if you have perfect absorber, which will have absorption coefficient equal to 1, you do expect your reverberation time to be 0, right? If all the sound energy that is incident is totally absorbed, then there should be no reverberation in that case. But if you calculate your reverberation time using Sabine's formula, then you get a finite number here, right? In feet, right? Or FPS system, we can say that, right? So if your alpha is equal to 1, you get a finite number over here. So that means your Sabine formula is not correct expression for alpha is equal to 1, which basically comes to the fact that your Sabine formula is actually not correct for higher value of absorption coefficient. And how much is that higher value of your absorption coefficient? Your Sabine formula is okay if your absorption coefficient is less than equal to 0.2. If your absorption coefficient is higher than this, then your Sabine formula over predicts your reverberation time. That is your limitation of Sabine formula. There is another expression which is called as Eyring formula. Let's talk about that, which gives you precise expression for reverberation time. Before we start ironing formula, if you have a room which has a certain volume, let's say that V is the volume of that room and S is the surface area. I'm going to retain small v for velocity of sound. Then it was found that statistically, again, the word statistics is very important because then it talks about like on an average. In a room which has volume V, surface area S, between any two successive reflections, your sound is going to travel on an average 4V upon S distance, which, let me write that the distance between your successive reflections and again, this has been proved statistically, is going to be this much. If your volume and surface area are in FPS system, then this will be feet. If your volume and surface area are in SI unit, then this would be in meter. So this is the distance between two successive reflections, which basically means that, let's say if your sound travels and there is, let's say first reflection, then second reflection, and then third reflection. So between second and third reflection, this much distance will be covered by sound. And between fifth and sixth reflection also, this much distance will be covered by sound. This is kind of average statistically that is obtained here. Now, if this is the distance between successive reflections, then can you calculate the time between successive reflections? Because we know what is the velocity of sound, right? Then I can calculate how much would be time between successive reflections. This would be your time, right? It's basically like now a time period. If you can talk about time period in this scenario, this is kind of time period. And inverse of time period is your frequency, right? And frequency is basically how many number of times an event is happening per second. That is how you define your frequency. So I can actually then say that if this is time between your successive reflections, then I can say that what would be my number of reflections per second? And again, if you say that this is your time period, then this is basically your frequency, which will be reciprocal of this number. And then this would be equal to this number over here. This is number of reflections that are happening per second. Now, let's say I want to calculate number of reflections in time t. Then this will be equal to SVT upon 4 times V. Again, I'm retaining this small v for the velocity of sound and a v is for the volume. If your volume and surface are in FPS system, you take velocity also in the same units. And if your surface area and volume are in SI units, you take velocity also in the same units. So let's stop it here for the time being. And let me deviate a bit from here. For example, you have a sound intensity incident in a room that has a large number of surfaces. Gautam, just a minute. Let me finish explaining this and then we'll take your doubt. For simplicity, let's say that your incident sound has intensity equal to 1. And the average absorption coefficient of this room was alpha bar, which basically means that now in this room, if there are 100 objects, I can take every absorption coefficient of each object equal to this number over here. Now, if 1 is the incident, then alpha bar of this will be absorbed and remaining will be reflected back. So you'll have 1 minus alpha bar, which will be reflected back. So after first reflection, you have this much intensity reflected back. Now on this surface, again, your alpha bar is the absorption coefficient. So whatever was the incident, alpha bar of that will be absorbed. Right? Now, if you talk about the reflected from here, how much would be reflected? Incident minus absorb will give you how much will be reflected, right? जितना आपका incident है उसमें से आप जितना absorb हो गया वो subtract कर देंगे तो आपके पास reflected आ जाएगा, which basically means that I'll have to do this minus alpha bar 1 minus alpha bar. If I take 1 minus alpha bar common here, you will have 1 here and minus alpha bar here, you will basically have 1 minus alpha bar squared. This much will be now your reflected intensity. Again, the next surface also has alpha bar absorption coefficient. On this surface, you have this much as the incident intensity, 1 minus alpha bar whole square. Out of that, now this much will be absorbed and remaining will be reflected back here. Again, if I want to calculate how much will be reflected here, I have the incident which is equal to this number here, and then I have reflected, I have absorbed, sorry, which is equal to this number here. 1 minus alpha bar whole square अगर आप बाहर कॉमन ले लेते हो तो आपके पास 1 minus alpha bar बच जाएगा, that which basically means that I can write it 1 minus alpha bar. Now this means that, and it will keep on going like this. So after first reflection, your reflected intensity was 1 minus alpha bar. After second, it will be 1 minus alpha bar square. After third, it will be 1 minus alpha bar cube. If there are n reflections, so after n reflections, your reflected intensity, if you talk about n reflections, your reflected will be 1 minus alpha bar raised to power n. We started with 1 as incident intensity. You can take it as I naught here. If you take it I naught here, your I naught will go everywhere. And then your after n reflections, your reflected intensity will become I naught into 1 minus alpha bar raised to power n. This will be your reflected intensity. We'll pick up from here in the next class because now we know how much will be your intensity after n reflections. Simply you have to take power n. Now we know how many were the number of reflections in time t. For these many number of reflections, let's say your intensity after time t would be equal to I naught 1 minus a bar raised to power number of reflections. And here your number of reflections is equal to SVT upon 4V. These many number of reflections are there. So we'll start from here in the next class. Let's take the couple of doubts quickly.
मैम वो limitations वाली slide का screenshot लेना था.
Limitations वाली slides का. Sure.
मैम.
हाँ जी बच्चे.
मैम आप एक बार दोबारा explain कर सकते हो repetition वाला part?
कौन सा part?
रिपीटेशन वाला पार्ट, इससे पिछला पार्ट,
इससे पीछे वाला
मतलब अभी जिसका इसने बोला स्क्रीनशॉट लेने के लिए
लिमिटेशन वाला.
हाँ
सो लिमिटेशन ऑफ सबीन
मैम, लिमिटेशन नहीं, रिपीटेशन वाला.
रिपीटेशन वाला यू मीन टू से ये वाला?
हाँ ये वाला मैम.
ये वाला, okay. So we are saying that, for example, you have a room and the average absorption coefficient of that room is given by this number here, alpha bar, which basically means that now we can say that every surface will have this much as your absorption coefficient. Let me draw this again quickly. Otherwise, it will be difficult. And I'll draw the less number of surfaces now. So let's say that you had incident intensity, which was equal to 1. Now we said that every surface has an absorption coefficient alpha bar. So your 1 times alpha bar will be your absorbed sound intensity by definition of alpha bar, right? We said alpha bar is equal to absorbed sound intensity, I'll not write the complete, divided by incident. Now your incident is 1, right? So your absorbed will be alpha bar here. Now, if you talk about your reflected intensity, you will have 1 minus alpha bar because your energy is conserved. Intensity is basically related to energy, right? Now this surface, for this particular surface, this is your incident intensity. Yeah. Those who don't have any doubts, they can leave the class now. So this is your incident intensity for this surface over here. Now this surface also has absorption coefficient alpha bar. Out of this incident intensity, your this much will be absorbed, and remaining will be reflected back to the next surface over here. You can calculate what is your remaining. Your remaining will be incident, which was this, minus absorb, which was this.
How we calculated the absorbed one?
हाँ जी बच्चे,
आपने यहाँ पे अल्फा बार into 1 minus अल्फा बार लिखा, वो समझ नहीं आया।
क्योंकि ये आपकी इंसिडेंट है, राइट? We define alpha as absorbed upon incident, right? अब आपकी incident you are saying is 1 minus alpha, yeah, alpha bar in this particular scenario. Then you can say that your absorbed will be equal to alpha bar into 1 minus alpha, right? Incident का आप absorption coefficient से multiply कर दोगे तो आपको absorbed intensity मिल जाएगी basically.
तो मैम फिर फर्स्ट केस में 1 माइनस अल्फा क्यों है, सिर्फ अल्फा क्यों नहीं है?
क्योंकि एब्जॉर्ब तो अल्फा है ना, ये रिफ्लेक्टेड है, दिस इज योर रिफ्लेक्टेड।
मैम
हाँ जी
मैम, जैसे पहले में इंसिडेंट था 1 और अब्सॉर्ब हुआ अल्फा बार,
हाँ जी,
तो रिफ्लेक्ट हुआ 1 माइनस अल्फा बार।
हाँ जी,
अभी नेक्स्ट में इंसिडेंट है 1 माइनस अल्फा बार और अल्फा बार होगा अब्सॉर्ब।
हाँ जी, अल्फा बार ऑफ इंसिडेंट।
ओके मैम,
Look at this expression here. The definition of absorption coefficient. Intensity that is absorbed divided by intensity that is incident. Incident का alpha bar absorb होगा आपका. So that is why you have alpha bar multiplied by the incident intensity. ये इस surface के लिए तो reflected है, but इस वाली surface के लिए तो ये incident हो गई ना, ये वाली जो है. So that is why. I think I need to end the lecture. Someone is going to sign it in. So in the next class, आप में से जो लोग रह गए हैं, we'll start with your doubts. Someone is going to really